Alright, we're going to do a video here on graphing a rational function with ends that grow, meaning they don't flatten out. So we're going to avoid the idea of what's called oblique asymptotes and just focus more on generic end behavior here. Um, Now, what we're going to do in order to graph this is we need a couple things. This is the simplified version of this function. Well, sorry, it's really not the simplified version. It's just not factored. What's useful with this version of the function is looking at the end behaviors. So, meaning as x gets big, the numerator is dominated by 2x cubed, and the denominator is dominated by x squared, the highest degree terms on both the top and the bottom. And with fractions, of course, if you can, you reduce this fraction, and as x gets big in the positive and the negative direction, this fraction reduces to 2x, which is to the first power. Okay, all of the x's on the bottom cancel, and with two of the x's on the top, leaving one behind. So the end behavior of this function behaves like y equals 2x, which is a linear function, a straight line, which grows on the right in the positive direction and grows on the left in the negative direction. Okay, so those are our end behaviors. Now, the other thing we need is the factored version of this to get our zeros and multiplicities, or number of sign changes at each zero. Okay, so when we do that, on top I can pull a 2x squared out, leaving behind an x plus 2. And on bottom, if I factor x squared minus 9, I get x plus 3 times x minus 3. And so x plus 2's to the first power, x plus 3's to the first power, x minus 3's to the first power, and x is to the second power. So those are the multiplicities of the zeros. So I'll set up my number line chart now. And on the number line I'll have my x values, and then above the number line I'll have my y values, which are dictated by this function, which is the same as this function over here, just not in a factored version. So I'm going to cut my number line at the zeros, which are 0, -2, -3, and +3. So the first one is -3. Then I've got -2. -1's not a 0. 0 is a 0. 1 is not a 0. 2 is not a 0, but 3 is a 0. So I'll list all my zeros there. And the multiplicities of these are circled in red, so that's going to help us. But let's go ahead and find the y values at these specific x values, these zeros. So if x is -3, that makes this guy 0. That makes x plus 3 0, which is on the bottom. So that's an undefined y value. If I plug it in, this whole fraction is undefined. If I plug in -2 for 0, that gives me x plus 2 turns into 0, which is on the top. And so that makes the whole fraction equal 0. If I plug in 0 for x, that makes x squared 0, which is on the top. So that makes the whole fraction equal 0. And finally, if I plug in 3 for x, that makes x minus 3 0, which is on the bottom. So the fraction, the y value, is undefined. Okay. Now, I'm going to go over here to my end behaviors, because those are going to tell me the y values on the left and right ends of my number line chart. So on the left end of my number line chart, my y values, according to my end behavior over here, my y values are negative. They're below the y-axis. And on the right end of my end behavior graph, my y values are positive. Okay? Now I'm going to use my multiplicities to determine the rest of my signs. So -3 came from x plus 3 to the first. That's an odd number of sign changes. or odd multiplicity. So that means that this sign is going to be different. So that means this is going to be a plus. Negative 2 came from x plus 2 to the first, which is also a multiplicity of 1, which is odd. So that's an odd number of sign changes. So this sign is going to be different as I cross over my negative 2. So my plus that I had before changes back to a minus in this region. Then as I cross over 0, that came from x squared, has a multiplicity of 2. So that's an even number of sign changes. So that means this sign as I cross over 0 is going to be the same. So that's going to be a minus in this region. Then finally 3 came from x minus 3 to the first, which is an odd, a multiplicity of 1. So that's an odd number of sign changes. So that means these signs should be different, and they are, so that's a good sign. It all worked out like we expected. Now, and by the way, if you don't like the multiplicities or the sign changes, you can simply plug in x values in each of these regions and calculate a y value. And you'll see that the signs of those will be the same. And when I say plug them in, of course I mean into the function here to get your y values. Alright, so let's translate this to a graph, okay? So my y-axis is when x is 0. So let's list 0. And I've got 1, 2, 3, negative 1, negative 2. And notice I'm only labeling the important zeros, okay? So whenever x is negative 3, our y value is undefined. So that means I can't have a y value at this x value. We'll kind of look at this to see if it's an asymptote later. Whenever x is negative 2, my y value is 0. So that gives me the ordered pair, negative 2 comma 0, which is right there. It's a point. Whenever x is 0, my y value is 0. So that gives me the ordered pair. When x is 0, y is 0. That's the point right here. And finally, whenever x is 3, my y value is undefined. So that means I don't get a point at x equals 3. So we'll look at that as well. Okay, the next thing I'm going to do is I like to work left to right. So I'm going to go to my left end, and I'm going to mimic that in my graph. So here's my left end behavior. And I know in this portion of my graph to the left of negative 3, my y values are negative. So they're all below the x-axis. So what happens as I move this way, right? As I move to the right and get closer to negative 3? Well, as x approaches negative 3, my denominator gets close to 0. And when I divide by something really tiny, I get a really big y value. So my y values, as I get close to negative 3, are really big, okay? Now, so as I get close to negative 3 on my graph down here, my y values have to get really big, but they have to be negative y values. So I'm going to get big negative y values as I get close to negative 3, so my graph's going to turn like that. And so x equals negative 3 is an asymptote, because my y values are getting big near it. Alright, now from the other side, I know that as x gets close to negative 3 from the right, my y values still get big, but now they're positive on the other side of negative 3. So that means I'm going to approach this asymptote in an upward direction. And what happens as I move to the right? Well, as I move to the right, I have to stay at positive y values above the x-axis. But at negative 2, I have to hit y equals 0. So that means my y values are getting smaller until I get to negative 2. Now after I cross over negative 2, my y values are immediately negative. They're below the x-axis. That means I'm dipping below the x-axis. And I have to stay below the x-axis until I get to x equals 0, at which point my y values go back to 0. So they're decreasing for a little bit, but at some point they have to come back up. And if you want to know any other y values, particular y values, again, plug in more x values to the function, the whole function, and calculate the exact y values. This is just a sketch. Now, as I pass 0, my y values go negative again. So I have to go below the x-axis, like this, and then I have to see what happens as I'm moving closer to 3, right? So as x goes to 3, x minus 3 gets close to 0, which is still in the denominator. So my denominator also gets close to 0, which means my y values get big again. So that means x equals 3 is an asymptote as well. And on my number line chart, to the left of 3, my y values are negative. So I come this way, and then I have to stay below the x-axis, but then my y values get really big in the negative direction as I get close to 3. So it looks like this. Okay? Now on the right side of 3, my y values still get big, but now they're positive y values. So that means I'm going to do this kind of thing as I get close to 3 from the right side. Now, what happens on, this is an end, right? This is the right end, so I have to use my right end behavior. So I have to stay above the x-axis. So it looks like I'm going to keep coming down, but I can't keep going down because I'll hit the x-axis. So eventually I've got to turn back up, and then I turn into my right end behavior. So my right end has to look like what I have over here. And my left end matches what I have over here as well. So this is a sketch of the graph. And again, to get more precise y values, you can always plug in x values to the function and actually calculate them. The cool thing about this technique is you don't have to do any of that. You're using end behaviors, zeros, and multiplicities to understand what the graph looks like. It's not a lot of point plotting.